Welcome to UGC's e-Pathshala lecture series on computer science. The subject is about Introduction to Visualization and the paper is on visualization techniques. Module 36. In today's module, we are going to look at tree and graph visualization. The learning objectives of this module are, we will introduce the concept of what a tree is, and you will also come to know what the various traditional tree data representation techniques. You will also learn about the graph data and the difficulties that arise in representing this kind of graph data, and you will also learn about the different types of tree and graph data layouts as such. The basics of tree data. A tree is actually defined as a set of nodes and edges. Every edge has a pair of nodes, the parent node as well as a child node. A child node can have only one parent node as such. Between any two nodes in the tree, there is only a unique path that exists. A tree is a network of connected nodes where there are no loops. The root node is a single node that has no parents associated with it. The leaf node are the nodes that have no children associated with them. And the depth of the tree is represented by the number of nodes from the root to the leaves. These are certain basic terminologies related to tree data. So this is an example of a tree visualization. While tree drawing algorithms are more theoretical, the tree visualization is going to be more applied in nature. So we will look at certain examples of different tree visualization method. This is one such methodology for visualizing a tree. You can see there is a parent node which is represented as A, which is given the name A, and this A has got child nodes B, C and D. Similarly, B has got a child node E. E is called as a leaf node of the entire tree. E, F, G, K, L, N and O represents the leaf nodes of the entire tree. A is called as a root node of the entire tree. The depth of the node is represented by the number of hops. If you look at the depth of E is 2 because the path is from A to B and B to E. And there is also one unique path from A to E, say from A to B and B to E. There exists only one unique path. If you look at this traditional tree layouts, there are various layouts that are possible. They are classical layout, which are, the traditional tree layout is looking like this. There are various classical layouts. If you look at this H tree layout, this is a H tree layout, which is a best tree for balanced trees. If you want to represent balanced trees, that can be represented in the form of a H tree layout. There is another view which is called as a radial view, which also tries to cluster all the nodes and show it in the form of a radial view. There is another one type of representation which is a balloon view, which is actually related to the 3D cone trees. So there are various types of tree visualization techniques. One is the indented layout, the dendrogram, the balloon trees, the hyperbolic tree and the 3D visualization cone trees. If you look at this indented layout, it tries to place all the items along vertically spaced rows. It tries to use the indentation to show the parent-child relationship. So if you look here, this is going to be my documents, is going to be the parent of all these things. Similarly, papers is a parent of bionetwork, biology and GraphDB mining. The example for indented layout, well-known example is a Windows Explorer. Some of the problems associated with this kind of indented layout is that it only shows a part of the tree and it has got a bad aspect ratio, that is, which is not going to be very space efficient. But still, it is a most popular approach that has been used by almost many graphic designers for visualization. The next one is a dendrogram, which essentially is a layered drawing. It has got bended orthogonal edges. The layering is actually done according to the leaves. All the leaves are on the same layer of the dendrogram. It is actually commonly used in bioinformatics to represent the result of hierarchical clustering, and it also tries to represent some kind of phylogenetic trees. So here you can see the root has got 2 children, and once again the leftmost child is divided into 2 child, and in turn which is going to be divided into so many children. Next type of representation is a balloon trees. This is a variation of a radial layout. As the circles here are drawn in the form of the children are drawn in the form of a circle centered with respect to the parent. So if you look at this E, you have the parent in the middle and you have all the child nodes which are being placed around this parent node. So it is effective on showing the tree data structure, and the cost is about the node details as such. So you can see the parent is actually situated at the center of all its children basically. This is a balloon representation. Next one is a hyperbolic tree representation. These are the 2 example hyperbolic tree representation. It simulates the distortion effect of the fisheye lens, and it tries to enlarge the focus and shrink the rest of the thing, which is actually also called as a focus plus context approach. We have learnt already that in the focus plus context approach, we try to focus to the objects of interest, and the context information is also shown along with the focused information, but in a much distorted view. The focus is shown as an enlarged view, whereas the context information is shown in the form of a shrinked view. That is your focus plus context and fisheye distortion technique. Here it uses various interaction techniques, and it can be combined with different layouts. In the case of 3D hyperbolic tree layout, you have projecting a graph one on a sphere, and it produces a similar distortion effect. This also uses a balloon tree drawing approach. The next 3D visualization of trees are the cone trees. So these are good examples of cone trees that are being drawn. The cone trees are a 3D extension of the 2D layered tree drawing methodology. The parent is at the tip of the cone, and its children are spaced equally at the bottom circle of the cone. Either the children can be either placed in a vertical manner, or they can be placed in a horizontal manner as such. The extension to 3D does not necessarily mean that more information can be displayed as such. There are lots of problems associated with these kind of 3D tree visualization or cone trees. One is a occlusion problem, where it is not possible for the viewer to see what is at the back. So the front part literally hides the back part of the cone as such. And there are a couple of problems associated with interaction as such. There are other 3D tree visualization techniques. One is a 3D polyplane tree visualization, where you have subtrees are placed on the planes, and you try to arrange these planes in the form of a 3D to reduce some kind of occlusions. So in this particular example, we can see a layered drawing is used within each plane. So here each plane represents the subtree as such. This is also another one example of a 3D layered tree. Here there is only one cone representation. On the layers are parallel circles on the surface. On the surface you place the layers in the form of parallel circles. Here the example shows various colors which tries to indicate various layers of the circle. So the rose color balls indicates the bottommost layer of the circle, and the blue color ball indicates the topmost layer of the circle as such. Another representation technique is a tree viewer technique. So in the case of a tree viewer, we try to visualize the trees in a form that closely resembles some kind of botanical trees. The root is the tree stem as such, and the non-leaf nodes are represented in the form of branches. The leaf nodes are represented as bulbs at the end of the branches. An example is a Unix comb directory, which is being represented in the form of a tree viewer. There is another kind of trees which are called as elastic hierarchical trees. Here it is a hybrid of node link diagrams and tree maps. It is a combination of node link as well as tree maps. Using the node link diagram inside a tree map produces lots of crossings as such. So in elastic hierarchies, we can see that you have the nodes as well as the links associated with the node, and along with it you have the tree map being inserted within this node link diagram as such. Another kind of tree is a collapsible cylindrical tree. This is a very good example of a collapsible cylindrical tree visualization. Here it follows a telescope metaphor, that is a set of nested triangles as such. A cylinder is basically constructed, a set of nested cylinders as such. A cylinder is basically constructed for the children of a node and it has smaller radius. This cylinder is nested and hidden within the cylinder which contains the parent. These kind of cylinders can be pulled out to the right of the parent cylinder, or it can be collapsed inside the parent cylinder, whichever is necessary as such. Only one path of hierarchy is visible at a time, and it is represented a number of ever decreasing size of cylinders. All the cylinders of level 1 nodes are shown in a horizontal fashion, like being put onto a stick. So here we can see the various levels of cylinders with the various radii which are being shown here, which can be put inside within one another. Thereby it is also called as collapsible cylindrical trees. Next is the tree map. There are various variations of tree map as such. One is a cushion tree map, which uses shading to identify the levels in a tree map. This is a tree map diagram. Later on we will come to know what a tree map is. Voronoi tree maps, which are similar idea but uses Voronoi diagram as partitions. The space does not have to be rectangular in nature in the case of Voronoi tree maps, because usually in the case of a tree map the space is represented as a rectangular space, whereas in the case of Voronoi tree maps we can see that the space is not represented as a rectangular space as such. There are 4 major tree visualization techniques as such. If we want to summarize, we can see that you have indented list, you have node link diagrams, you have layered diagrams, and you have tree maps which are being represented. This is an indented list, this is a node link diagram, this one is a layered diagram, and the other one is a tree map diagram. There is another kind of visualization which is a very specific kind of visualization for a tree, which is called as a ball and stick visualization. So this ball and stick visualization uses the position and appearance of the glyphs to represent the nodes as such. So this is a tree layout of a FFmpeg software as such. This is a radial tree layout of this MPEG software. This is a ball and stick visualization. This is a radial tree layout. This is a bubble tree layout of the same MPEG software. This is a 3D cone tree layout of the same MPEG software. Here we can see the various layers are represented as different cones with different various radii. Next one is a tree map visualization technique. In tree map method, we have seen that we try to visualize the tree structure that use virtually every pixel of the display space to convey some kind of information. Every subtree is represented by a rectangle, and that is partitioned into smaller rectangles which corresponds to its children. The position of the slicing line determines the relative sizes of the child rectangles. For every child, we try to repeat the slicing recursively, thereby swapping the slicing direction from vertical to horizontal or vice versa. The pros and cons of tree maps are the benefits. It provides a single view of the entire tree, and it is easier to spot large and small nodes as such in a tree map. Problem is difficult to accurately learn the depth information. This is a tree map approach of the FFmpeg software. So in the tree map we can see the various layers which are represented as different rectangles and which are also nested inside different rectangles. This is an improved tree map which uses squarified layout and shaded cushion rendering approach. This is a node link tree where the nodes are distributed in space connected by straight or curved lines, and the typical approach is to use the 2D space to break apart the breadth as well as the depth information. They use a Ringfold-Telford algorithm for generating these kind of node link trees, and these kind of trees can be generated within linear time. This is a radial tree layout which places a root in the center of the entire layout, and the radius encodes the depth information. Other node link trees are also represented like this. You have thread arcs, you have phyllo trees. There are various layered diagrams which try to signify the tree structure using layering, adjacency and alignment. These all involve the use of recursive subdivision of a space which can apply the same set of approach as in the case of node link diagrams. So, these are layered diagrams which tries to use a recursive approach. So, this is an example of a icicle tree and this is a sunburst example which is shown in the form of a radial view. You have the hyperbolic tree browser wherein you have the view in the form of an hyperbolic trees. This is another one interesting example of a tree structure which is called degree of interest trees. Based on the degree of interest, each and every node is being expanded and it shows the various details. So, this actually represents the organization chart as such. If we want to know the details of each and every node, we can just go to that particular node and click on it. You will get the entire information about that particular node based on the interest of the user. The next one is a graph visualization. Graphs are the most general type of relational data set. Similar to a tree, it consists of nodes as well as edges. Whereas different from a tree, a child node may have multiple parent nodes in the case of a graph, and a graph can also contain loops or multiple paths between two nodes in the graph. So, if you look at the graph visualization, there are two different representations for graphs. One is a node link diagram, the other one is a matrix diagram. Usually, the node link layouts are being used popularly, whereas which has got some kind of scalability issues, and that is being solved by the matrix based representation of the graphs. So, if you look at the graph drawing and the graph visualization, graph drawing is an old methodology that is being followed in various books. It may have other goals other than visualization. Example is VLSI design. Whereas in graph visualization, we look at the size is a major issue in graph visualization. Usability needs to be considered and navigation should also be considered in the case of graph visualization. What about the node information in the graph? Sometimes a size or an importance is represented in the form of a node. The navigational system may have links to data. Glyphs are also represented. They are mentioned as a representation of higher levels in hierarchical clustering. The focus on graph is on structure-based properties and it is application independent. Some of the examples of graph visualizations are class browsers, entity relationship diagrams, real-time systems, that is in the case of state transition diagram, VLSI circuit design, circuit schematics rather than actual design, document management system, web navigation and virtual reality, which is a scene graph. If you look at the history of graph drawing algorithms, we can see that Euler used a drawing to solve the Königsberger problem in the year 1736. Later on in 1992, in a symposium, we had a graph drawing initiative. Then we looked at the issues of graph drawing. Some of the issues in graph drawing are planarity, and there should not be any edge crossing in the case of 2D graph drawings. There are aesthetic rules that are supposed to be followed in the graph drawing approaches. Edges should have the same length. Edges should be represented as straight lines, and isomorphic substructures are displayed in an equivalent fashion. The tasks related to graph drawing are layering a graph, turning a graph into directed acyclic graph, planarizing the graph, that is achieving that there are no edge crossings in the graph, minimizing the area, minimizing the number of beds and edges, and algorithms are, but some of the algorithms that are used for all these tasks are very complex, that too particularly for large graphs. One of the major problem in graph drawing or graph visualization is the size of the graph. So, how is it possible to represent some thousands of nodes in the screen which is of some size x cross y? So, some of the solutions to this are 3D graph drawing approaches. Non-Euclidean geometry can be applied, that is in the case of hyperbolic trees, non-Euclidean geometry is being applied to represent the entire graph. They can reduce the size of the graph. They can only show a part of the graph or blow up the part of the graph which is of interest to the end user. Some of the other problems related to navigation in graph data is predictability. The other one is the time complexity, the real-time interaction. So this is a layout of directed graph which is being represented using layerings. Here in this graph, this has been taken from this URL that is given here. Here in this graph, you can see that there are 11 crossings as such. So here there is a crossing, here there is a crossing, here you have so many crossings. So if you count, there are 11 crossings as such for this set of nodes that are being represented here. So we go in for a specific kind of approach which is called as a spring layout approach in the graph drawing algorithms. So these spring layout approach is a force directed approach. Here the nodes are being modeled as physical bodies that are connected through some kind of springs which are actually the edges of the graph. There is a high time complexity associated with this which is of order O of n power 3, and it is also not predictable in the case of spring layout. You have something called as spanning trees which are where you don't insist on the planarity of the graph, and these kind of spanning trees also don't worry about the edge crossings. These kind of graphs can be visualized through minimum spanning trees. Additional edges can be added later to these kind of spanning trees. It is a very common technique that is being used to represent the entire graph data. It helps to some extent with predictability issues, and the visualization for these kind of spanning trees depends on the starting point. 3D techniques are also applied to the graph data to visualize the graph data as such. The benefits of these kind of 3D techniques are it gains more, there is a gain in the space as such, and the humans are being familiar with 3D as such. Some of the problems associated with this are missing the motion as well. Some of the problems associated with 2D displays are missing motion and stereo cues, and it can be better solved by better technology as such. So if you look at the examples of 3D techniques, so here this is a 3D version of a radial tree. This is an example of an info cube, which a 3D info cube that is being visualized in this way. This is a fly-through representation of a two-dimensional representation which actually shows the SGI file system navigator. This is here the size represents the file size as such. This is similar to that of something called as a perspective wall that we have already seen in the case of distortion techniques. So in the case of perspective wall, which uses the focus plus context approach, we can see that the focused part is shown as a clear wall to the end user, whereas the context information is shown in the form of a distorted wall to the end user. The other name given to this is called as a perspective wall. You also have hyperbolic layouts, as in the case of trees. For graphs, we also have something called as hyperbolic layouts. Examples are web content viewers. It can be either in 2D or 3D. These kind of hyperbolic layouts are similar to fisheye lenses, and there is a possibility of interacting with large trees. So this is a hyperbolic viewer. So you have the example at this particular URL. These are various URLs which shows these kind of hyperbolic viewers. This is a 3D hyperbolic viewer. Some of the concepts associated with these hyperbolic viewers are, for a given point, a non-intersecting line, there are many parallel lines that pass through this particular point. Segments that are congruent in the hyperbolic sense are exponentially smaller in the Euclidean sense. When we approach the perimeter, they are projective in the case of clean model, and they are shown as straight lines which are suitable for 4x4 matrix based graphics. They are conformal, or they follow the conformal or Poincare model. Straight lines are drawn as arcs in the case of Poincare model, and the angles are drawn correctly in Euclidean sense, and they are computationally more demanding. So if you look at the clean model as well as a Poincare model, this is the left hand side represents a clean model where you can see the edges are represented as straight lines, whereas here the edges are represented as arcs as such. So this is taken from this particular citation. If you look at the navigation and interaction associated with graphs, There are various navigation and interaction patterns that are associated with the graph data as such. You can zoom and pan for the graph data. You can zoom for graphs where you can actually go in for exact, not pixel based approach, that is adjustment with respect to the screen transformations. You can have something called as geometrical zooming. You can have simple blow up of the graph data. You can have semantic blow up of the zooming of the graph data. You can have content changes. You can do clustering of the graph data. The problem that is associated with combining the zoom and the pan are, assume that you are going to zoom and pan independent. So the objects may be temporarily moving away. So the solution is a space scale diagram where you have the semantic zoom. The picture differs for each layer. If you look at the semantic zooming, you can see that the picture is differing with respect to various layers as such. This is a focus plus context technique that is being applied to visualize the graph data as such. Here the zooming loses the contextual information. The focus plus context keeps some kind of context information. Examples of this are fisheye views and distorted views. This is a fisheye distortion. You try to pick up a focus point and map the points within the radius using a concave monotonic function. So this is an example for this is Sarkar-Brown distortion function, which can be applied as a concave monotonic function within a particular radius. The problem with this kind of fisheye approach is that the distortion should also be applied to links. So when we try to apply these kind of distortion techniques to the links, they become prohibitively slow. Alternate is to continue using lines and can result in unintended line crossings as such. Some of the other alternatives for applying the distortion techniques to links are combine the layout with focus plus context layout. You can have something like a hyperbolic viewer, or you can have various other combinations, possible combinations like balloon view with focus dependent radii. Some of the incremental exploration and navigation techniques associated with the graph data type are, for very large graphs, you try to display only a small portion of it, and the other parts are displayed as and when they are needed. The displayed graph is going to be small. The layout and interaction times may be small. Example is taken from this particular website. Clustering can also be done with respect to the graphs. So you can have something called as structure-based clustering, and they are most common in graph visualization. They try to retain the structure of the graph, and they are useful for user orientation as such. You can also go in for something called as content-based clustering, where they are going to be more application specific and can be used for filtering and search. Filtering is removal of elements from the view, and search is emphasis of an element or group of elements as such. The common goal of clustering is to find the disjoint cluster. You can also try to clump them, that is finding the overlapping clusters. So the common technique that is used is least number of edges between the neighbors. So here this is a hierarchical, follows a hierarchical clustering approach. Successive application of clustering processes can be navigated as a tree. So this is another visualization of higher layers. Here the glyphs are being used. If you look at the node metrics, using the node, it is possible for us to give ranking to the nodes, measure certain abstract features. Edge metrics can also be used. They are structure based or content based. You can talk about the degree of the node as such, how many number of in links and out links from that particular node that can be counted. Methods of representing unselected nodes are ghosting, that is de-emphasizing or relegating nodes to the background. This is a ghosting approach. Other one is hiding approach, not displaying the nodes at all. The second figure shows a hiding approach. The other one is a grouping approach, which tries to group under a super node representation. So the third figure follows a grouping approach. This is a hierarchical graph which shows the evolution of the Unix operating system as such. There is something called as a force-directed layout visualization, which is specifically applied for a graph. This principle is used to minimize the energy of the layout. The physical analogy is that every node in the graph is a charged electrical particle and every edge is an elastic spring. The nodes are connected by edges and will exert an attraction force. All nodes will exert a rippling force on each other regardless of whether they are connected or not, and for each node we try to calculate the total force acting upon it. We try to move the position of the node along the direction of the force. We try to do this process for each and every node, and we repeat the above force directed movement in an iterative manner until it tries to converge us into a layout that has minimal forces for the nodes and thus the minimal energy of the layout. So the output that you get will be of this format, which is a call graph which is being generated using a force directed layout. So these are some of the example graphs that are drawn using the force directed layout. This is a splatting technique which shows a dense representation. To summarize, in this module we have learnt about what a tree data structure is and how is it possible for us to traditionally represent the tree data. There are the different types of tree data visualization techniques. We also looked at the various representation techniques of graph data as such, the difficulties that arise in representing the graph data visualization, and various graph data layouts are also being studied as such. Thank you.